All right. You see the screen okay? All right, hang on just a second and we'll get going. Okay, just had to take care of something there real quick. Let's go ahead and get started. So our last couple of days we've been talking about what they call translations of functions. And that means moving them left and right and then up and down. And to move them left and right, you just tack a number on at the end. If it's a positive number, you go up. If it's a negative number, you go down. Okay? Now, for stretches and compressions, think about what the words themselves mean. To compress something means to push down on it, to like squash it down. Okay? So in terms of a function, a compression means the function is getting pushed down. It's taking longer for that function to get moving, to like go up or go down, that sort of thing. And then obviously when you stretch, you make something longer. So what you can think of there is if you stretch the function, then you're like pulling the function up or pulling the function down so it moves faster. Okay, so that's the basic idea of what we got here. And we're going to talk about how that can be accomplished by changing some numbers around. So that's where we're at today. Okay. Let's go ahead and get going. All right, so it says, oh, and then the other thing we can do is reflect. I forgot to mention that. So reflection here. A reflection, quite simply, is just to change the signs on our function that we've got. Okay, so let's go ahead and get our good friend Desmos going here. And we'll talk about this one here and how you do a reflection. So let's go ahead and bring Desmos up here. All right, so you see we were doing some absolute value in one of the other classes. All right, so that was x squared minus 3, right? Okay, so I said you had to switch the signs on the functions, right? So if I did that, so we go, so what we're looking for is a mirror image along the x-axis, so the horizontal axis. So think of the x-axis as being a mirror, okay? So we had to switch the sign, right? So we know if we switch the sign in front of the x squared, then it's gonna flip and go downward, right? So there we've got that. But that's not exactly a mirror image, is it? And if I make this minus 3, so I changed just the sign on the x squared, but not on the 3 at this point, right? So yeah, we've got a mirror image here, but the mirror image, the mirror would be like laying right here. Okay, so the mirror would be at x equals -3. We want a mirror image around this guy, so that means we have to also switch this guy's sign as well. So make him plus. I'll try anyway. Let's try plus sign. Still not it. Now we've got a mirror image, don't we? So this looks like this one, and it's reflected around this guy right here. So we have to change the signs on all the terms, which is pretty easy, right? So then for this guy, what we've shown is all we have to do is switch the signs on all our terms, right? So this will become minus x squared and then plus 3. So basically what you do to do a reflection is change the signs on all the terms of the function. Okay. So this guy, we can keep it all together here. So this guy would just be minus the absolute value of 5x. Or not 5x, 2x plus 5. There we go. Okay. So let's take a quick look at what that would be like. All right. Go ahead and I've already forgotten what it was. That's not it. Okay, so 2x plus 5. All right, so we do absolute value. So there's our V shape, right? So for this guy, just to flip it around, we just put the negative sign out front. You don't have to like change the signs on the inside. You can see we've got the mirror image thing going on. Okay. So for something like that, you can just stick the minus sign out front. Okay. Oops, that was our last exciting episode. Let's get rid of him. Bring back our other guy. Okay. So then the same thing here. We would just change this guy to positive square root of 2x. And then over here, we would just switch this to positive x and minus 4. Okay? So reflections are pretty easy. Just switch all the signs. And when it's grouped together like it is with the absolute value, you can just put the sign in the front and you're good to go. Okay? Questions? Alrighty. So let's continue on. Okay, so this says, tell whether the graph of G is a vertical or horizontal compression or stretch of the graph of F. Okay. So the first one here, we've got the absolute value of x plus 3. So based on what we've seen so far, that would be a V-shaped graph, right? Absolute values are V-shapes, right? And since we have plus 3, that means we would move our V-shaped graph over 3 units to the left, right? So again, a stretch is when it's like you grab the ends of the graph and you pull it upward. And I think that's what we've got going on here. So by putting the 2 out front, we will make our graph go up faster. So that would be considered a vertical stretch. Okay? So let's take a quick look at that. All right, so we've already got this guy here. So it was x plus 3, I believe. We don't need another x. X plus 3. Okay, so there's our guy. And then this guy would be minus x plus 3. There's our mirror image again, right? So that's if we did a minus, but we don't have a minus. We've got a 2 this time, right? So let's change him into a 2, and you see what happened there. The graph, let's bring it down here a little bit so we can see it better. The graph of the original guy in red is now going up twice as fast. So think of it like you grabbed a hold of the red graph and pulled it up, and it becomes the blue graph because it's going up twice as fast. So this would be considered a vertical stretch. Okay, so in order to get a vertical stretch, you put a number out in front of the function. Now in this case, you could actually have it inside as well. But notice then it shifted over a little bit, didn't it? So it's not quite the same. So you just need to leave the number out front. So when you have an absolute value, or maybe you have like parentheses with a squared thing going on, then just throw a number in the front and you're good to go. All right. All right, so let's take a look at the next guy. So he's got x squared, right, minus 4. And then they made this 0.5x. So right away, 0.5 is less than 1. So if you have a number between 0 and 1, this is when you're going to get a compression. This means your number's not going to go up as fast, right? So this means it's going to push the graph down this time. So that's what's going on there. So let's go ahead and take a look at these guys then. All right. So this time, let's go ahead and just clear these guys out. I've got x squared, and I already forgot it. X squared minus 4. Okay. So x squared minus 4. So it's going to drop us down 4. Let's center this a little bit better again. All right, then the other guy, we had 0. Well, we need a parenthesis. Hang on. 0. X. That guy. Square him. And then the minus 4. So you see what's happened here. The original graph here in green got pushed down or kind of spread out, okay? So there's 2 ways you can think about this. Usually we talk about a vertical compression, right? So vertical means we're pushing the graph down, right? This could also be called a horizontal stretch, which means you're grabbing the graph and pulling it out horizontally. Excuse me. Okay, so yeah. So you can think of it as 2 ways. We're either pushing the graph downward, or we're grabbing the graph and pulling it out side to side. So a vertical stretch and a horizontal compression are basically the same thing. Thank you, Chloe. Okay? But again, if you have a number out front that is between 0 and 1, obviously more than 0, because if you have 0, you got nothing. So if you have like a fraction or a decimal that is less than 1, then you're going to get the compression, the vertical compression. Okay. And obviously if the number goes negative, then that flips us around, and that's the reflection that we talked about at the beginning. Okay. So that's what we got going on there. All right, back to our regular scheduled program. Okay, so that takes care of those two guys. So in the first one, we have a vertical stretch. Here we have a vertical compression. And just to kind of keep it simple, I usually just talk about it in terms of the vertical stuff. We don't usually get into the horizontal stuff too much. I mean, just be aware that that's another way of saying it, but normally we'll just stick with the vertical to keep it simple. Questions? Alrighty, let's go and check out a few more. Okay, so again, same thing. Here we've got a square root function, right? Okay, and here we've got a square root function, but we've got a number out front that is a decimal between 0 and 1. So this guy is going to be a vertical compression, right? It's not going to go up as fast. That's what the 0.25 tells us. And again, just to get the vibe for what it looks like. There we go. All right. So this time we're going to have a square root function. Let's just go clear these guys out. All right. So we've got square root. And once again, I forgot. Plus 1. Okay. So x plus 1. Now notice that's different. That's not what we want. That's actually moving the graph up. We want this guy to stay underneath here. There we go. That moves us back 1. So notice if it's under the square root, it moved us back 1. If it's outside the square root, it moved us up 1. So that's a key difference there. Okay, so then the same thing we got here, we're going to have 0.2, that's a comma, hang on. Right, and then we'll go square root of x 1, that's 2. Still a 2. Okay, so you can see now that our graph got pushed down, right? So here's our original in black. And then when we go to the red graph, it's like we grabbed onto this graph and pushed it down. So this would be a vertical compression. Does that make sense? And if we put a number bigger than 1 in front of that, then it would stretch the graph and it would pull it up. So once again, our good friend Desmos comes in very handy. Yep, sure do. That's what I say. You can just Google Desmos. This will come up. It'll bring up this graph that looks just like this, and then you can come over here and you can plug in whatever you want. If you come down here, it's this little keypad thing. This gives you, like, if you wanted something like squared or like x to whatever power you want. So you would like here, you know, just to give you a little tutorial on this. So you could say, okay, well, here's x squared, right? Let's say I wanted x to the third. Then I would go x, and then I'd hit this guy, and then you can key in any number you want. So there's an x to the third. Okay, and here's your square root. And then if you need numbers, you got them over here, plus, minus, divide, all that good stuff. So it's pretty easy to work with. There's a couple little quirks to it. I think we found one the other day when I had to do like 2 to the x plus 4 or something like that. We had to put a little parenthesis in for the exponent so it knew to take that along with the exponent. But yeah, it's a pretty neat little program for this kind of stuff. Okay. All right. So let's go back to what we were doing. There we go. Okay, so here's a cube root. We had just talked about this kind of stuff. There's a cube root function. We'll show you that one as well. So again, this one will give us a stretch, but it'll also kind of move us over. So it's a little bit different, but let's take a look at this guy. All right, so in order to find, this one's a little tricky. In order to find like a cube root thing, we have to go over here where it says functions. And there it is right there under miscellaneous. So there's all kinds of stuff. I mean, I don't even know what this stuff is here, to be honest. I have no idea what that stuff is. This stuff down here I kind of get. All right, so we go ahead and grab this guy. Now notice that we have a cursor up there where we can put in for the cube root. So then we've got the cube root of x and minus. Okay. So in order to be a true stretch, we need to put the 2 out front. So this one will look a little different, but I think it shifts us around a little bit too. So let's try that one. All right, so back over here. And there's this guy. So yeah, you got to tinker around. Sometimes you got to look for some stuff. But for the most part, it's pretty easy. And then this one was 2x. And then minus 1. Okay, so we did get a bit of a stretch, but we also got to move over to be a pure just stretch, because this actually moved us back a little bit, as you can see. Okay, so to get a true stretch, so this one, while it is a stretch, it's not just a stretch, it's also being translated over to the left. So a true stretch in this case would be, let's do the cube root thing again. So that would be cube root of x. Wow, I didn't know you could do that. So x minus 1. Okay, and then if you put a 2 out front, that's a true stretch. Because notice we kind of are at the same point, and all we've done is stretch this up, stretch this down. Well, the one in purple did get a little bit of a stretch, but then it got moved back as well. And the reason for that is because it took the cube root of 2 here. Here it would not take the cube root of 2 because the 2 is on the outside. So is this one technically a stretch? No, it's not just a stretch. The guy in black is a true stretch. Okay, so that's a little bit funky. So if they put the number under here, it's going to change it, but it's not going to be just a stretch, because then they take the cube root of 2. Here, this is exactly like this, except we're now multiplying it by 2, so we're stretching it up by a factor of 2. Does that make sense? Kind of a technicality, I know. Okay. So to be a true stretch, it's just a number on the outside multiplied by whatever you had originally. See this, like I said, again, the one in purple actually changed the position of it as well, not just the stretching. So to be a true stretch, you just stick a number out front, okay? And everything else stays the same, like it did in the green one and the black one. Cool. All right, so that guy, is a pure stretch? No. A little bit of a technical issue there. All right, so let's check out these guys. So this one changes the slope, but if you leave this number alone, that's the same y-intercept. So here we've got a slope of 1, here we've got a slope of 0.4. So this one will be considered a compression because we haven't moved the position of anything. Okay, so let's take a quick look at that one. All right, so let's get rid of these guys. All right, so we had x minus 3. So there's a line, and again it crosses at 0.3. And the next one is 0.4, and then x minus. So again, you can see on this one, we didn't change positions. We still crossed at the same spot, but we took the graph in red and pushed it down so it doesn't go up as fast. So as long as it's not under like square roots and cube roots and stuff like that, just changing this number here, but leaving this number alone is going to change the slope, which is like a compression, but we haven't changed the position. It hasn't moved left or right. Okay. So that one would be a vertical compression again. Okay. Okay, so then this guy, same deal. We've got the exact same thing here, but we put a 2/3 out front. So this guy will also be a compression. Okay. Let's take a peek at that. There and there. And I think +2, if I remember right. Okay. Oh, -2. See, I didn't remember right. Okay, so instead of moving us 2 to the left, it'll move us 2 to the right. Oh. And then this one just took a 2/3 out front. So let's go ahead and do this. We'll put in our original guy here. So and then up front. And the way you can do this on Desmos is we would go, I think this is how you do fractions on here. You go 2 divided by 3. So you see how it turned it into a fraction, which is pretty cool. And I'm always telling you fractions are fancy versions of division problems. So we got a little bit of a compression here, right? So here's the original guy in red, right? And then when you go to the guy in blue, notice we have pushed the graph down a little bit. So again, this would be a vertical compression because again, you have a number that is between 0 and 1, but positive, okay? So just a fraction pushes it down, a number bigger than 1 will push it up. Make sense? Sweet. All right. Do one more here and call it a day. Okay, so this guy again, we're going to have x squared plus 2. So let's go ahead and do that. X squared plus, here's our guy. And then our new guy was 6x. And then plus 12. Ooh, where'd he go? All right, so I have to move him down a little bit. All right, so again, we do have a stretch going on here, right? But we also shifted up from 2 here to 12 here. So this is more than just a stretch. So notice on the last one, we stayed at -3 in both cases. So that was a pure stretch. This one is a stretch, but it's also a vertical shift up. In order to be a true stretch, this guy would have had to have remained that's a true stretch. Okay? So we still would have the same starting point when we go up faster. This is strictly a stretch. But by doing this, then we also have a shift upward. Okay? So that's the difference between those two. Let's go back and look at them for a second. Okay. Oops. Yeah, this is it. So here, if this would have been +2, then we'd have had a pure stretch. But this one, we multiplied everybody by 6, right? So that's why I pulled it up as well. Questions? Okay, so the next one is going to be a stretch. Now normally, like I said, we have the guys out here, but since we don't have any shifts going on in here, this will just be basically multiplying by the square root of 7, which is, somewhere between 2 and 3. Okay, you actually take the square root of 7. So if we did that real quick, I'll get my calculator to come up here. So if we just did 7 and square rooted it, 2.6. Okay, so let's take a look at what those guys look like, and then we'll call it a day. All right, so let's go back to Des. All right, so we've got one is just the square root of x. From their square root and our x. So there's that guy. And then this guy here. Square root of 7x. All right, so let's take a look here. Got to move our graph around so we can see what's going on. There we go. So again, this has the same starting point. So as you can see, we know that this graph was going to be about it's going to go up about 2.6 times faster. So that's what we got going on here. So that's why this guy's getting pulled up as opposed to the guy in red. Okay, so this would definitely be a vertical stretch. It's only when you have numbers underneath in addition to the variable that you get sort of the movement around. But that's the best way to check it for sure, is if you put it on Desmos and you get like the same starting point, except that one graph's been pulled up or down, then you have a true compression or stretch. Okay? All right, guys, well, that's probably a pretty good stopping point for today. So again, thank you guys for showing up. I've got attendance already. And we'll see you tomorrow, hopefully.